Problem 11, we're given the function e of t equals 3,861 minus 77.2t, and this models the surface elevation in feet above sea level of Lake Powell t years after 1999. The model is only accurate from 1999 to 2004. So part A wants us to use the table feature of our calculator to help complete the table below for the function. Then we're going to graph the results and decide if it would make sense to connect the data points on the graph. So let's go to our graphing calculators, and you're going to start from the home screen, enter y equals, and then we're going to enter 3,861 minus 77.2, in this case x. And let's go to our table set and make sure that our table is set up the way we want it. We have a table start. Mine is at 4. Yours might be different. I'm going to change that to 0. My table is changing in increments of 1, and my independent and dependent are both set to auto. So that's what I want. So then I'm going to press second and then table to give me my table results. So at 0, I have 3,861. So I'm just going to write each of these into the table. So you might want to pause the video and do that, and then come back and double check. Once the values are all written into the table, then we're asked to graph the results and decide if it would make sense to connect the data points on the graph. So we can use our graphing calculator, and let's go to the window. Our x-min should be 0. So our x values travel from 0 to 5. So x max is going to be 5. Then y min, we can go ahead and start that at 0. And y max, our vertical intercept is 3,861. This is a decreasing linear function, so I want to be sure and see that 3,861. I'm going to make my y max 4,000. And then I'm going to press graph and see what happens. So there's the function. It is linear. It doesn't really look like it because of the steps in our graph are so far apart. Let's go back to window, and all of the action in the outputs is really happening between 4,000 at the top end and 3,450 at the bottom end. So I'm going to change my y min to 3,450, press graph, and that gives me a much nicer shape. So what I'm going to do now is to transcribe that information using the ordered pairs here onto the grid here. You might want to pause the video and do the same, and then come back and check your results. So transcribing the information from the graph on your calculator to the paper takes a little bit of work because the grid needs to have increments that are equal distant. So I use these little squiggly lines to be able to start. This is actually 3,475 here, and I went up to 3,875 at the top here, and then just labeled every 100 increments. And plotted the points, labeled them, labeled the axes. So your graph should look something like this. We see that it is, in fact, a linear function. We can see that clearly from the image. So let's go to part B, identify the vertical intercept of the linear function, which is 0, 3,861, 3,861. Written as an ordered pair, it's labeled already on the graph. And in a complete sentence, what this means is the starting elevation of Lake Powell in 1999 was 3,861 feet. So you can see that sentence written out here. Part C, determine E of 2. E of 2, we can look right at our table. When the input is 2, the output is 3,706.6, and let's write that as a complete sentence. So in a complete sentence, we can write the elevation of Lake Powell in 2001, because that's what the t-value of 2 represents, was 3,706.6 feet. And one thing that we didn't address back in our graph was if it makes sense to connect the data points. And it really does, because we can measure the surface elevation of the lake during the year. We don't have to wait at the endpoints of the years. So we can gather data all along, each month or every day for that matter. So it does make sense to connect the points on the graph. All right, going back to part D, it says identify the slope of the linear function. Write a sentence explaining its meaning. Be sure to use a complete sentence and include all appropriate units. So the slope is the coefficient of t, which is negative 77.2. Notice I'm not including the t, just the value, the coefficient of t. And I'm going to write this in a sentence what this means. The slope is negative, meaning that we are losing surface elevation every year in Lake Powell. And so let's write that information in a sentence. So writing all the information out, we have the surface elevation of Lake Powell decreased at a rate of 77.2 feet per year from 1999 to 2004. Notice, because we're using the word decrease here, decreased actually, we do not put the negative in front of the 77.2. So the last part, E, says determine the practical domain and practical range, use inequality notation, and include units. So the practical domain, I'm just going to call PD, is the entire set of input values that we can use inside this function. And we know that time goes from 0 to 5, and that is years. So my inputs start at 0 years and go all the way up to 5 years. So this is our practical domain for this function. Our practical range is the set of outputs that we're going to use, or we are able to use in the function. Now this is a little bit different than the way you might think about it. So the outputs go from 3,861 to 3,475, but the way we write our inequality is from left to right, so we need to put the smallest value first. So our practical range then goes from 3,475, 3,475, and that is feet. And the variable is E. We can write the whole function notation, E of t. And the top value for the range is 3,861 feet. So just be sure that you write your values in the correct order using the inequality notation.